Okay, so the remainder of the chapter focuses on cellular automata, which actually come into play in some areas as systems of randomness in games, but also um, just as interesting objects of study in their own right. Instead of starting with their simple one-dimensional automata, I want to do a quick search for Conway's Game of Life, which is mentioned later in the chapter. And I think that Evernote's inserting some pieces here. But if you're paying very close attention to this area by my cursor, you see something kind of strange happening on the Google page. And you can see it's behind here as well. I'm going to pause this and see if there's any way to get Evernote to not render. If I could just get the web clipper to turn off. Anyway, you see this pattern of squares. I'm stepping through that. These squares are implementing Conway's Game of Life in the background of the web page on the search results of Conway's Game of Life. Let's see if we can get this to run. I'm going to open up the glider example and click Start, and maybe up the speed a little bit. Make the grid a little smaller. Okay. What is making this pattern move across the grid? It looks to be a fairly complex and organized model, but in reality, Conway's Game of Life is much simpler than that. The rules are right here. We have a two-dimensional grid. A two-dimensional grid here is a two-dimensional array. When John Conway proposed this, computers were not easily accessible, so I believe he used like Go stones on a Go board in order to test this out. But as we got computers that could model this, it became much more easy to see what iterations of the rule set would bring. And the rules are basically this. If there is a cell that is turned on, and let me make those bigger, if it is alive, if the cell has one or no neighbors, it dies of solitude. If a cell has more than 4 neighbors, it dies of overpopulation. But if it has 2 or 3 neighbors, it survives to the next iteration. So in this setup, this cell has 1 neighbor turned on, it will die. This cell has 2 neighbors, it will survive. This cell has 1 neighbor, it will die. Okay, if that were the only set of rules, it wouldn't be very interesting. Eventually things would all lose neighbors and die of solitude. But there's also a way for life to be regenerated inside of this grid. If you are an empty cell and you have exactly 3 neighbors, on the next iteration, new life spawns. So this is an object called a spinner. This cell has 2 neighbors alive, and the neighborhood are the 8 cells immediately surrounding it. So this cell has just 2 neighbors alive. This cell has 3 neighbors alive, so the next iteration that cell comes alive. This cell has 2 neighbors. This cell has 2 neighbors. This cell has 3 neighbors. Next iteration, that one will come alive. And then this one only has 2 neighbors. So if I click Start, what ends up is this pattern repeatedly spins. It changes from horizontal to vertical, and on the next step it goes from vertical back to horizontal because of those rules. Now, that's why a glider is really interesting because let me actually choose an exploder. Based on these rules, this sort of behavior is created across the grid. And so now we've reached what appears to be a somewhat steady state. If we start with just 10 cells in a row and apply those rules, it ends up doing this. And then some patterns, like this, the Gosper glider gun, is very interesting because what ends up happening is these things bounce back and forth and generate gliders that will go off at regular intervals, all based on just these simple rules right here. So this is where cellular automata kind of come from in their mathematical underpinnings. So with that as a precursor, we can model this inside of an array, and the first example is just a one-dimensional array in a one-dimensional cellular automata. So we have an array of cells, and the cell is either on or off, and we're going to change that state on the basis of simple rules, and we want these changes to be determined by neighboring cells so that eventually the cells will grow out. So I'm going to come back over to BlueJ, close down my log analyzer, bring up version 1 of the cellular automata. And so we have two classes, the actual automaton and then a controller class. And I am going to start with, let's say, 15 cells. Okay. Now, what's going to happen is each line is a new iteration. So I'm going to tell this to step, and as a result of this first iteration, new life is formed on the basis of the rules in this automata. Then I go ahead and I step again, and the pattern of cells changes on the basis of that, and I can tell it to step again, and the pattern gets updated, and I'm going to have it run 5 more steps. And so over time, this pattern of cells starts to look like it has some greater intent inside of it. Let me run another 15 steps and see if we can get things repeated. So it looks like because we have a 15 cell array, we are going to get a common pattern that's going to repeat over time. Let me clear this one, and I'm going to try a new, and let's just change the number of cells to 14 and have it run 30 steps. And the pattern has a different shape as a result of that. Okay, so this cellular automata project, what it's basically doing is it's going through the array and figuring out for the next step, ask for the location that I am currently in and the one immediately before it and the one immediately after it. Add those 3 values together and then take the integer remainder when we divide by 2. So if there's a 1, we print a plus sign. If there is a 0, we don't. And so the next state for this, the edges are special cases because this one doesn't have anything to the left and this one doesn't have anything to the right. So what we can do is we can look in the code. Okay, let's open up the automaton and see how the automaton works. In this instance, we look at the update. At the start of the update, we take a new variable called next state, which is an array of integer types, And we're going to allocate the memory by calling the new operator, saying that we need an integer array, and it is the same length as the state array. So instead of having a hard-coded value in here, we ask the size of the array that currently exists, what is your length, and use that to create an array that can mimic it. We then need to figure out what is in the position in the current state so that we can set up the left, center, and right variables so we can assign the value for the next state. So we're going to go through for every position in the current state, and we have to figure out what is the value for the left, center, and right for a given value. So over here, if we're in position 0, there is no left, so we'll just say that that's 0. So we're going to cap things at the edge. If we're over here at the right, there is no right to this, so we'll say that this value, the value for right, is also 0. So we're going to put the boundaries in place mathematically. So what we want to do, back into the code, I equals 0 as long as I is less than the length of the array. Come back into the code for the loop and create variables left, center, and right. If I is 0, there is nothing left of it, so we're just going to say that the left value is empty. If I is not 0, then ask the current state array to give us the value that is in I minus 1, which could be a 0 or a 1, and we're going to put that into our left variable. Then the center, the object that we're currently looking at, is whatever the value of the state array is at I, and that on the right hand side, if I plus 1 is less than the length of the state array, then we can actually go to the right in the state array and get the value that's at I plus 1 and set that to right. But if we're all the way over here at the right edge, I plus 1 will be greater than the length, and so we're just going to say that the right value is 0, that there is no cell that has a value to the right, and so it shouldn't impact the formula. Okay, so we set up the values for left, center, and right. Then we add left plus center plus right and take mod 2, and that becomes the value for the next state array. So coming back to this for a moment, our first time through the loop, I is 0, and I want to do this probably with a square object or a rectangle object. And let me go ahead and do it like that and make the fill none. Okay. If I equals 0, and ignore the step column, this is not part of our grid cells. I is 0, so we're going to look left. There is no left. We look for the value here. That's center, that's right. We do our calculation and set the value next. I plus plus, we come over, and now we look left, we look center, we look right, we do the calculation, that becomes that value. I plus plus, we're here. Center right, 0 plus 0 plus 0 mod 2 is that value. Then we start getting interesting. Left, center, right. 0 plus 0 plus 1 equals 1. 1 mod 2 leaves a remainder of 1. That becomes our plus. We move right. Left, center, right. 0 plus 1 plus 0 equals 1. 1 mod 2 is 1, and that becomes our value. I++, we move over. 1 left, center, right. 1 plus 0 plus 0 is 1. 1 mod 2 is 1. That cell gets turned on. And I++, and we move over, and we can see 0, 0, 0, 0 mod 2. We get to here, where I is state.length minus 1. So we're still less than state. We have left, we have center. Right is the same as, is greater than the edge of the array. So this empty cell is 0. 0 plus 0 plus 0 is 0. Mod 2 is 0. And so ultimately we figured out what the next line is after we've processed the entire array in the manner that I just demonstrated there. So please keep in mind that in order to figure out the next state, we have to do a lot of work in the array over and over and over again in order to figure out what's happening. Okay? Back to the code. We take that value, we set that to next state sub I. Eventually we drop out of the for loop, and right before we leave the for loop, we say that, okay, we figured out what the next state is. Now, put that entire array into what used to be the state array, or what is the state array, because as we leave this update, what used to be the next state is now the current state. So we're going to do the same thing when we come back in, only this time state is here. And we do the same process all the way across, and we end up with this state. So next state becomes state, and then we come here, and we do the same process. And as a result of that relatively simple rule, we get interesting differentiation within the lines. If we want to reset our array and get things starting again, notice that this is our static call to the arrays class. So tell the arrays static class to run the fill method. Here is my array, and fill everything with a 0. Then, after we have all zeros, take the number of cells, which is the size of the array, divide that by 2. Take that slot in the array and put a 1 in there, because we need something in order to seed the initial pattern. But notice that this is, because we're using a static method, it's not state.fill, because it's not an array object. We're going to have to use the arrays class and tell the arrays class method or static method to run. Okay. So there is our automaton. There are other versions of the automaton in the chapter. And one version of the automaton uses a special operator, which is sometimes called the ternary operator and sometimes called the conditional operator. It's basically an if-else all done on one line. So the pattern is have some Boolean condition, question mark, what do you do if it's true, colon, what do you do if it's false? So here is one way to look at that. We're going through the for loop for each cell value in our state array, which is an integer. If our cell value is equal to 1, print a plus. If it is not equal to 1, print a space. It is sometimes a useful operator. You shouldn't use it just to use it, but it's very handy for things like print statements where you can get one of two values chosen to be put into the output, so you should know that it exists. Okay, a little bit about cellular automatons and the automaton project. Let's wrap this section up, and then we just have to talk about two-dimensional arrays, and then we're done with Chapter 7.